My screen is also visible.
Yes, sir.
So in last class, somewhere we were talking about the first caselet, fitness first. You guys must be able to recall what we were doing. Yeah.
Yes, sir.
So we could not finish. We were somewhere here, if you remember. Till last class, we finished up to this point. Only two things in the last is left. So if anyone would like to ask anything. Anyone would like to ask anything?
So how do we calculate heteroscedasticity in eViews? I think we did not cover that.
eViews, let's concentrate on one software, don't you worry.
Okay.
Multiple softwares will complicate only.
Okay.
So right now, pay attention to understanding that if there is heteroscedasticity, how it is going to impact the result, and how to go for correcting the problem. Suppose there is heteroscedasticity, then what should we do? Did we discuss this part in last class?
So we did, for starter, we have to use robust, like regression,
Correct,
weight, height,
correct.
age, comma,
Yeah,
robust.
correct. So that is good enough to start with. Don't you worry.
Okay.
At some later stage, if time permits, I'll give you idea about eViews also.
Okay.
So don't you worry. Just concentrate on understanding. Software is not that big thing. In the sense, you have got so many software. So conceptual clarity will always help you. But if you are conceptually not clear, then no software will do any help.
Yes, sir.
If you want, I can show you.
So actually, I just wanted to see how, whether
No issue. That's
like
okay.
how the output looks.
Your inquisitiveness is perfectly all right. I think we have got 10 observations, if I remember. Yeah, we have got 10 observations. Three checks right there. Go to quick, and this way we can have. Right, and we'll go for estimating the equation, estimate equation. We were interested in knowing the weight, height, and age. Is this okay?
Yes, sir.
So this is the output we have got, and if you compare, you will find that outputs are same. Yeah, same outputs. Unstandardized coefficients we always talk about, so these are same. So when we have to go for, we call it coefficient diagnostics, and within that you will find residual. Yeah, residual diagnostic will give you heteroscedasticity test. Yeah. So here, Bruce-Pagan or White, I think in Strata we have gone for Bruce-Pagan. So, or White is also very popular. We can also test the White test for heteroscedasticity in Strata. Yeah, multiple things can be done. So, for example, I have just gone for testing the white test. Null remains same. If you recall, null was no heteroscedasticity. And if null is rejected, then we'll say that heteroscedasticity is there. If you look at just look at the first F statistics, and this is the p-value. If you remember me, p-value will not be always explicitly present, but if you pay little attention, you can easily find out where the p-value. So this is the probability. So this is the p-value. And as you are finding that this value is more than 0.05. So we'll say that the assumption of no heteroscedasticity cannot be rejected because the p-value is less than 0.05. I hope point is clear.
Yes, sir.
Null hypothesis is, you can also look here, null hypothesis, homoscedasticity is nothing but no heteroscedasticity. So
Yes,
no heteroscedasticity assumption cannot be, the null of no heteroscedasticity or homoscedasticity cannot be rejected. So we'll say that the R data has got no problem. This is what we have interpreted here. The results are different, maybe Bushpanang. That's not important what test we are applying, but you'll find that whichever test you apply, if null is rejected, then there is heteroscedasticity. If it is not rejected, then it is the problem of heteroscedasticity is not there in the model. The same thing is coming in. We
Okay,
can
sir.
also go for trying the Bushpanang, I guess. This might be giving more or less same value, not exactly same because softwares run the formulas differently. They have their own method to normalize things, but partly we are finding the values are not exactly same, but results are same. So nothing to as such worry.
Okay, sir.
Yeah. Any other query? Yeah. Any other query? So there was a long gap because of your summer internship and all. So finally we are back. And this is what we have done. This is the caselet we were trying to do. We were trying to find out the association between weight, height, and age. How height and age are going to impact on the weight. That was the basic idea if we look at the first question in the caselet. And we haven't come to the second part. Second part is more towards going for prediction. So we'll come to it, finish the. And if you recall, I have told you there are three things which we need to do. Pro forma or some style of reporting the information. First was descriptive. Second is what we are doing is still midway. And third is discussion. So this was the first table which we were supposed to make, descriptive statistics. And if you recall, first was all the variables we have taken irrespective of dependent or independent. And we have just find out the correlation coefficient. And we have again given you idea if correlation coefficient null is rho is equal to 0. If you remember, we have discussed that the null hypothesis of correlation coefficient test is that there is no correlation or rho is or R is equal to 0. And if the results of correlation coefficient is coming out to be significant, means p-value when we run the correlation coefficient is less than 0.05, we will say that correlation coefficient is significant. These were the cases when we have got asterisk here. Asterisk means the result is having a p-value which is less than 0.05. So we call it significant at 5%. So significance issue is very well part of correlation coefficient also. And this is what we have done in our previous classes. And we have found that only height and weight have got significant correlation, that too of the range of 0.80. And that's it. There is no other variable which has got issues. So this is the descriptive statistics. Second table, we are on the way. Third, we talked about reporting the results. So this is what we were partly developing. So today we'll obviously close this caselet. We'll move to two more caselets quickly. We'll go for tire track and CEO salary, and then I'll give you one more caselet for home later on. Before you have the next class, you can do that on your own. I'll give you the solutions also. Solution means all these three tables, 2 table and 1 discussion of output. All 3 things will be available for the 4th caselet, which is I can just show you. So mutual fund caselet, I have kept it for you to do it on your own. Today we are here with the we'll finish fitness first, and we'll try that these 2 more caselets, tire tracks and this CEO salary. We'll try to finish using the same pattern. We'll fill the 2 tables and 1 output discussion. So let's complete the fitness first caselet.
Hello, sir.
Yeah, tell me.
Yeah, Nishant here. Sir, I have a question. There is one point which I am still not clear on. So, this with regard to the test of significance which you had done earlier. So, when I was reviewing the videos, that time what I observed is that in the test of significance, we are trying to find out that we are looking at the independent variables, and we are trying to find out whether these independent variables, how much of the impact, or whether they're significant to impact the dependent variable. This is what was my understanding of that test of significance.
Perfectly all right, Nishant.
Right. So my query is, someone can always argue that since this data which you have taken is based on a sample itself, it is not the population, it's a sample. Someone can always argue that the sample is not representative of the population. So are we conducting any other test to find out whether the sample itself is representative of the population?
Sampling distribution is part of research methodology. You will have that type of discussion there. Normally, what we assume when we say that we are using the data, that sample is randomized. So random sample we assume, that is one. Sample size is the second thing. And as long as these 2 things are holding true, we say that our data is correct. So questioning of data is something at this point, or when you are practically doing something, you have to believe that the source of data is correct and the process of collecting the data gathering is also correct. So as such, in statistical or econometrical approach, we do not have as such any test by which we can talk about the data, whether data is great or not. In primary survey, we have got something known as reliability Cronbach alpha. So that we find out, but in secondary data, we do not have such issues. Rather, we'll have 1 or 2 issues which I'll try to handle in CEO caselet. There, what happened that the variables which you are having, they have disparity. Like one on the scale of thousands, other is on the scale of 1 or 2 or up to 10. So that type of things can be handled with the help of log transformation. So if you take the log of high denominated data, then you will find that lower denominated data and the log values of high denominated data will be comparable. So at times results are improved. So log transformation is one trick which we at times do. We do call it data cleaning. So practically when you run the regression analysis, you get to know a rough idea because you look at mean and SD, and I have not added 2-3 more things. If I want, I can add like minima, maxima, kurtosis, skewness. So when we go for descriptive statistics, sometimes we plot the data also to have a feel of whether the data is seemingly correct or not. In general, it is correct or not. So these are some of the approaches which we resort to know whether the data is up to the mark. But as such, there is no statistical test to understand whether data is of appropriate quality or not. Yeah, Nishan, you're there?
Yeah, I'm here. So my point is that there are methods to find out whether the data itself is correct representative of the population. It's just that we are not covering that in the syllabus right now. It is if I'm not wrong, in business stats or in research methodology, we might cover that concept.
No.
Am I right?
As such, no. Reliability of the data is something which we do in primary survey. I mean, primary data. Right now, we can say that partly we have got, but reliability, Cronbach alpha, usually we do in interval scale when we measure the data. So I don't think so. I'll check if you want to know whether some statistical test is there or not. Anugamni, I'll check with her if she has got or she is discussing something or she has some idea. I mean, to my mind, I don't recall anything statistically which we can do to understand whether the data is up to the mark or not. You understand?
Yeah, actually,
So
I
primary
got this
survey
idea
has
because
got
I was reading some other books. So that is why in those
no,
books
but
it was
if you can
mentioned
tell
that
me the context, the type of data, what type of data, primary data or secondary data?
it would be a primary data. So
So same thing I'm telling you. These issues are much more relevant for primary data. But when we use econometrics, so we mainly follow the secondary data. I mean, for example, primary data, when you ask for opinion, then people might differ in their statements. But when you are taking their weight or height, so that is something which is not subjective, which is fixed. Though it may be collected for the purpose, so technically that is a primary data, but the data is not behavioral in nature. So data issues normally in the secondary data is not there, or in econometric studies, we normally do not have any such problem. But we obviously go for cleaning of the data. Cleaning of the data, we ensure that, as I told you, log transformation is one of the examples by which we try to settle the data. So this issue can be handled as the case come. But in general, there is, to my understanding, there is no method by which sampling issues. Sampling issues are there with the prime data than the secondary data.
okay, thank you, sir.
But I'll check. If I find something, I'll surely share with you. I'll speak to Nugamini if she has something to, I mean, we can have some discussion. I can surely pass it on to you.
Yes, sir, that would be fine because I was thinking from point of view of maybe if someone is doing a
But
research.
secondary data, there's no. You just Google my name, you will find that number of papers which I have. So that's not a problem. Research, but thing is that data-wise, secondary-wise, we do not have issues of the authenticity of data, because weight will be weight, height will be height. We can't have any subjectivity element as part of that. Issues are maybe large sample, small sample, whether the randomization is there, representation is there or not. These issues might be there, but in secondary data, we do not have such issues. I'll get back to you, Nishant, if I find something.
Thank you, sir.
Yeah, I'm open if you have, anyone has got any other follow-up thing. Okay. So we were talking about finishing the table. This is the table. And we were talking about, if you remember last classes, we had these two independent variables. We looked at their standardized and unstandardized coefficients. We had a discussion, the difference between unstandardized and standardized. So unstandardized is the basic coefficients used for modeling, and standardized regression coefficients are meant for comparing the strength or involvement of independent variable in the regression model. Higher the value, absolute value, obviously, better or larger the impact of that particular. So suppose I compare here, then I'll say that height is more important than age. So this is in addition to the issues of significance. So standard coefficient helps in giving you the comparative picture of different independent variables, and it makes sense only when you have more than one independent variable. When you have one, there's no issue of comparing, but when you have more than one, or I say multiple regression, so when you have multiple regression, then we have the issue of having the standardized coefficient. SET, statistics, p-value, we have done all those discussion. These things are clear. And by the time when we have finished this much portion, we said that we have to talk about diagnostic testing, which we call. Why we call diagnostic testing? Because the estimation of these coefficients are based upon certain logics. And we have discussed that we have got one logic or methodology, you can say, which is optimum least square. So OLS methodology, optimum least square, or OLS. So OLS methodology depends upon certain assumptions. There are 6-7 assumptions are there. And the important among them, which we surely take care when we are running a regression model, is these three: heteroscedasticity, and we have got autocorrelation, and we have got multicollinearity. So right now, if you recall at some point of time or the other, I would have definitely talked with you that right now the data which we are using, data can be divided into type of data. If we say, then I can say that I have got cross-sectional data, I have got time series data, and I have got panel data. So right now, the discussion which we are doing is cross-sectional. Cross-sectional means at a particular point of time, we have got the values of different variables. Right now, when we are saying cross-sectional, then in this data set, which we have used for fitness first, we have got weight and height at a particular or age at a particular point of time. So when we do the discussion at a particular point of time, we are talking about cross-sectional. As we move to next chapter, we are right now doing regression analysis chapter. Next chapter, I mean, I can say this is second, third chapter will be dummy variable regression. And then we'll move to ARIMA modeling, which is nothing but the forecasting type thing. So as we move here, we'll talk about this type of data. So when we talk about time series data, then this issue of autocorrelation will come into picture. So for time being, we are just keeping it reserved for a long discussion as we move to next chapter, as we move to fourth chapter after dummy variable regression. So we are here right now. Panel data, we have last three topics on panel data. So we'll be covering panel data there. So that's why autocorrelation right now we can knock out and we can ignore for timing. If we remove this for discussion in a cross-sectional data, I repeat myself, when you have cross-sectional data, you can remove the testing of autocorrelation. Autocorrelation is not an issue. So the only thing which is left, if you remember, I have discussed three things in the diagnostic testing. First was heteroscedasticity. Second is autocorrelation, as I said. Right now we are not talking because we are not talking the time series data. And then we talked about multicollinearity. We'll right now discuss. And then we have got fourth issue, specification. Specification means whether the number of variable. Nishant was having a question on sampling. But when we have econometrics or problems on econometrics, we lay more emphasis on this issue in specification because it creates the issues and sampling as such doesn't come into picture that much in secondary data or in econometrics based applications. So multicollinearity right now we usually don't discuss here multicollinearity because multicollinearity, if you remember, we discussed that we may discuss this later on. So it is nothing but variance inflation factor. We call it variance. This is not coming. Leave it. It is variance inflation factor. So this can also be VIF. Right now we are talking about multicollinearity. So out of these three, we are talking about multicollinearity. Multicollinearity is a very interesting concept. It says that the independent variables should be correlated with each other. I repeat myself, the concept of multicollinearity says that when you are trying to find out some association of independent variable with the dependent variable, then the independent variables may have correlation among themselves. That's not a problem. But the correlation should not be beyond a certain level. If correlation crosses that level, then there is a problem of multicollinearity. I repeat myself. When we are running the regression and we are making use of OLS, then I close this. So multicollinearity will be a problem when we are having the application of OLS in the regression analysis. So multicollinearity is a very simple thing that it says the correlation between let's say I say x1 and x2, both are independent variable, it should be less than 0.8 and significant. So if I give you in words what exactly I'm saying, that correlation between x1 and x2 is something which is acceptable, but that correlation should be less than 0.8. It will be a problem only when correlation, when it is problem, that is more important thing, when it is a problem. So it will be a problem when correlation coefficient between x1 and x2, x1, x2 are representative of any two independent variable if it is more than 0.8 and significant. Even if it is more than 0.8 but it is not significant, that type of correlation between the independent variable is not a problem. So correlation among independent variable is something which is taken for granted, but that correlation should not be too high, and a number has been fixed partly that it should not be more than 0.8, and obviously significance. If it is more than 0.8 but not significant, which is not usually the case, you will find that when correlation coefficient is more than 0.8, in good number of occasions, rather 80-90% chances are there that would be significant, because the significance of correlation coefficient is designed in such a way that higher the value of correlation coefficient will be having more probability that it would be significant. So technically we'll say correlation between independent variable, if it is more than 0.8 and significant, then only there's a problem of multicollinearity. Multicollinearity problem, this will be explained in the output. We have got multicollinearity option. Why I'm writing this optional? Because unless until you have got more than one variable, more than one independent variable, only then multicollinearity issue comes. Multicollinearity is there when you have got more than one independent variable. If there is only one, there's no problem of multicollinearity. There is no issue of multicollinearity per se. So right now, if I look at the descriptive, look at here in descriptive, and what we are having, this weight is the dependent variable and height is the independent variable, and there is a correlation coefficient which is significant. So that's not a matter of concern for us. What is a matter of concern? We have got two independent variable, height and age, and what we are trying to find out, what is the correlation coefficient between height and age. So if you look at height and age, this is 0.24. Number one, it is less than 0.8. Minus, plus minus, that's not important. Absolute value, if you remember, correlation coefficient takes values from -1 to +1. So when we say multicollinearity, we are talking about 0.8 in absolute sense. So keeping that thing in mind, this correlation coefficient between age and height is 0.24, which is less than 0.8. This is number one, and second, it is not significant. So as a conclusion, we'll say there is no problem of multicollinearity in the data. Anyone has got any clarification? Anyone needs any more clarification? Is it okay? So I'll say there is no problem of multicollinearity collinearity in the data. So this thing can be done with the help of VIF. There is a VIF, as you are finding in eViews. What we have done, we have just run the model. After running the model, we need to go to View, Coefficient Diagnostic, and you will find Variance Inflation Factor. So variance inflation factor, as you are finding, so this value, as you are finding, it is only for independent variables. So this variance inflation factor value should not be normally more than 4. If it is more than 4, we say if VIF value is more than 4, some people say 6. To be a little conservative, I can say that VIF value of 4 or more may have a problem of multipolarity. But I always suggest that whenever you are testing multicollinearity, it is always good to go by the basic idea of finding out the correlation coefficient between the independent variables. If the correlation coefficient is more than, VIF is secondary, it's not primary. The primary thing is correlation coefficient. So if I have to just write down the value, I can write down 1.058, HT 1.058, 1.058. I think there is a rounding off issue. And then we have got 1.59 again for age also 1.05. These are the values of VIF. Independent variable, there is no problem of. We have variance inflation factor. So now this table is completed. Now we have complete descriptive statistics table with the value of VIF and a brief discussion on multicollinearity. Anyone has got any doubt? Clarity on multicollinearity? I repeat myself, multicollinearity is a problem when correlation coefficient between independent variable, even if there are 4 independent variables and the problem is between 2, because correlation coefficient is always between 2, and if the correlation coefficient is more than 0.8 and significant, then there is a problem and we need to check. Otherwise, correlation coefficient which is less than 0.8, whether significant or non-significant, that's not a problem, and that does not amount to multicollinearity problem. If there is a multicollinearity problem, then again the coefficient values will be questionable. It is much more bigger problem than heteroscedasticity or autocorrelation, as it will come. We'll see in the ARIMA model. So multicollinearity is a bigger problem. It creates much more trouble as compared to heteroscedasticity or autocorrelation. But unless until correlation coefficient is less than 0.8, no problem. When it is more than 0.8, only then it is a problem. Yeah, shall we move to next thing?
Sir, I have a doubt.
Tell me.
Yes, sir. So, if there is a multicollinearity problem in the data, so how does it affect the findings? Like, for example, the independent variable, if the relation between them is more than 0.8 and it is also significant, so to what extent and how does it affect our weight? That is a dependent variable.
What happened in such case? Suppose we would have got between height and age correlation coefficient of more than 0.8 and significant. Then what we need to do when we are running the model, we are supposed to take one of them away. It means why it has to be done that way? Because both of them are so much closely associated that presence of both of them in the model can create trouble. So we try to take out one and we try to look at the standard error, in which conditions standard errors are going down, correlation, these adjusted R square is going up, and overall significance of the model is coming better. So what happened when you remove the variables which are having the problem of multicollinearity, then you have to hit and try and see which one is giving a better model. So one of them is supposed to be removed. That is the idea. If you talk about remedial action, the way I told that if you have got HT or autocorrelation problem, go for robust estimate. Similarly, when you are having multicollinearity problem, then you are supposed to remove one of the two variables which are having the multicollinearity problem. I hope I have answered your question.
Yes, sir. Yes, sir. Thank you.
Any other thing which you want to add?
No, sir. No, sir. So, and sir, while selecting the variable, do we give importance to the standardized coefficient in order to remove the multicollinearity?
No. Rather, it is practically hit and trial. When these issues are there in the data, first of all, you understand what is the problem. Suppose there are two variables which are having the correlation coefficient which is more than 0.8. So what is the problem? Problem is that you have not made your model in a appropriate way. When I say appropriate way means you have a dependent variable and you should have independent variable. So you have not selected the independent variable in the right way, means your theory of trying to predict the dependent variable is not correct. So if I use a technical word, we call it a specification problem. If you pay attention to what I discuss quite often, specification problem. So whether it is multicollinearity, autocorrelation or heteroscedasticity, though the approaches of these problems, the way we detect the problems are different. ST is detected differently, autocorrelation is detected differently, machine multicollinearity is detected differently. But the common reason for all these problems is specification error. So when you have two variables, independent variables having high correlation coefficient, you are having in your model, it means your construction of your model or the selection of independent variable is not right. So that's practically specification problem.
Okay, sir. Got it, sir. Thank you.
I would welcome more questions. Feel free if you have anything doubt, please raise your hand. I mean, just unmute and speak. Today we are having one small quiz, and most probably Karka sir will give me a class tomorrow. So tomorrow after the class, even if there is class or there is no class, I'll give you one assignment which you have to complete within a week. So practically we are achieving that regression we are winding up today. So every big topic gets over, then we have one component of evaluation. So you will have assignment. Assignment will be based upon completely regression analysis. So a good number of you will get plenty of occasions because when we have variety of cases, so as per the requirement of a case, you might have such issues. So struggle yourself and you can always get back to me. And then we can have a more such discussion that how to handle problems of violation of assumptions or problems of specification. So when you do it, then you will be better off in terms of understanding how to detect them and how to rectify them and how to make best use of the available information or best use of the theory which you are using to build a model. When you want to make a model, there has to be a logic why you are doing it. So when you are doing it, then you know that what you can do, what you can't do. Then limitations come. So point here is that when you do it on your own, you will be better off in understanding these issues, detecting and rectifying the problems. So you will enjoy once you move to the assignment. So on Sunday by Sunday, you will surely have, and time will be of 1 week. So you can use all your understanding to make the or complete the assignment. That will be individually. I'll give you assignment to all of you. So no teams, individual assignments, and individually you have to submit. So coming
Sir,
back, yeah.
Sir, as you explained the multicollinearity thing, like one statement of what multicollinearity deals with, sir, can you tell about the heteroscedasticity also once? Like, what is actually we are dealing with?
Heteroscedasticity is basically, when we are running the OLS or when we are estimating the coefficients of regression equation using optimum least square method, then it is based upon certain assumptions. So one of the assumption is, and when I say assumption, that assumption is basically of the error term. What is error term? We have discussed error term is
Y minus Y cap equals to
y
ET.
actual minus y estimated will give you error term. Error. Suppose this is I, then all are of I. Are with me? So what happened? We have got, suppose we have got 10 observations. So we will be having I from 1 to 10. So what happened? This is important thing, because this is something, if you recall me, uh, this
Makes
is the
sense.
problem. What is this? This is the, if you remember, I told you why we are taking, then
Unobserved.
this is the model, the regression model, and this is the error term, right? So this becomes the observed, or which what we have modeled, and this is something which is unobserved. So we have not been able to model this. So what happened when we go for diagnostic testing or look at the up to what extent model was able to capture the variation in this with the help of variation in the independent variable. So this tells us the story that up to what extent we have done the job well, or we have not done the job well. So if I have to define heteroscedasticity, I define that variance of U, error term, you're with me, condition to the
Yes, sir.
independent variable xj.
The
I'm
standard
trying to make
deviation
it
that
hard.
you
This
explained.
should be constant. So
Okay, sir.
variance error term variance. Conditional variance means for a particular independent variable, whatever is the series of error terms they are coming, the variance of that should be constant. And we have discussed, I vaguely remember, if it varies, because when we calculate the values of beta, j's, all these coefficients, when we calculate, then that depends upon some assumptions regarding the variance
Yes, sir.
of
I
the model.
remember the T test and F test that you discussed about, that it depends
Everywhere.
on sigma, and if it is not constant, then it's a
It
problem.
is not constant, then you will have varying. So estimation will have problem. So estimator, which we call blue, best linear blue unbiased estimator. So OLS should be blue. Just you are asking something, so I'm trying to give you a little more information. So blue, we call the estimator should be blue, means best linear unbiased estimator. So this will have issues when this is not constant. So blue is the requirement of OLS estimator. So optimal require estimator. So this is the estimator to calculate the beta coefficient. So that will have the issue. So one liner, if you want, you can say that the conditional variance of error term should be constant. I repeat, when you run a regression, then conditional variance of error term should be constant. I hope I've given you one liner.
Yes, sir. So if the
This is the one
conditional
liner which
variance is, if the conditional variance
conditional
is not
variance
constant,
of error term should be
yes.
constant. This is one line.
So,
If you
sir,
want.
if the conditional variance of error is not constant, then we have heteroscedasticity problem.
Correct.
Okay, thank you, sir.
And if there's a problem, it means estimation will have issues. Yeah, I would strongly encourage people to ask questions. Anyone else has got any issue, please feel free in asking. Yeah. So coming back to, now we are coming to last test, which is known as reset test. Reset test is a test of specification. Let me come back to reviews starter so that we continue with the so this is what we have, and we have just run regression, RE regress, and weight, and then independent variable HT and age, and this is what we have got. This is what we have got. And if I want to go for specification test, what I'm doing right now, I'm talking about specification part of diagnostic testing. This test says that null, again, we have to go by the null. Null says here, the null is that there is no problem of no specification problem. This is the null. Alternate Yes, there is. Yes, is problem of specification. Though this test is not very great test, but always we say something is better than nothing. So we go for reset test. So E start OV test. We go for, after running the regression, we go for restart OV test, and null, as I have discussed with you, null is there's no problem of specification. And right now when I have test the OV test, answer test, and this probability is coming out to be more than 0.05, so null of no specification problem cannot be rejected. We'll say that our model which we have made has got no problem or specification error. Are you with me? So I can put the values from the test. This is 0.36, 0.36 in bracket. I'm putting all the time. One more habit we can start doing whenever the p-value is less than 0.05, we can show with the help of asterisk so that it is significant at 5% level of significance. There is no other result. F test is significant. As you can see, p-value is less than 0.05. So I'm putting a asterisk. You remember we have got this. Again, we can see F test. This is the F test of the model, and this is the p-value 0.012. 0.012 is less than 0.05. So that's why this 8.67 it is coming from here. If you can recall, this is the output of regression. Output regression. This is the output regression. This is the F test of model 8.67, and this is the corresponding p-value which is less than 0.05. So we'll say that F test is significant. That's why we said that model is perfect. If you remember, null of F test was model is perfect, and model has issues, and the alternate was model is perfect. So just because the F test is having p-value which is less than 0.05, so null of model is not fit is rejected, and we'll say that model is perfect. So that was the interpretation of F test. So there is no other place where we need to put the asterisk. So with this, with the reset test, we can complete our discussion of regression analysis. You want, I can show you here also. It can be stability test, and we have got Ramsey reset test. Fitted values, put 2, and you will find the F statistics. Again, you are finding this is the value and this is the probability, which is again more than 0.05. So null is same, that there is no problem of specification, no specification problem. And that is it. I'll again show you how we test this in eViews. We run the model, go to view and stability diagnostic, and there we have got reset test. So we have got something like F statistics, which is not significant or having the p-value which is more than 0.05. So null of no specification problem cannot be rejected, and we are saying that model does not have any problem of specification. So parametric stability will say that our model does not have problem or does not have a specification problem. So in this discussion of output, whatever input is there in the table, because when you share the information with someone, you are sharing both the tables, descriptive and regression table, and then you are having this commentary so that you can corroborate or explain whatever is there in the table, and you can have a couple of more words or lines you can add as and when you explain in this discussion of output. We are discussing what are the outputs which are there in the tables. So up to now we have discussed. So we have talked about, if you remember, we were having 5 points discussion. Coefficient analysis we have done. Model interpretation, we have done 3 things we discussed. Diagnostic testing also we have completed right now. And we have next thing, as we were discussing off and on, that the problem of specification is the key problem which we come across when we talk about econometrics model. So the theory behind model formation is the most important thing. It is not that we have got some data. What happened nowadays? People have got data, they have got software, they put the data and try to get some idea. That is not the good thing to do. Thing is that you should have a problem which you are trying to solve. So problem can be solved with the help of some theoretical background, that weight can be related to age and height. So there's a theory, at least common sense, and then we have got data and we are trying to run the model. So something, just because availability of data doesn't mean that we can run a model and get to have some data and we talk. No. So specification is the key thing when we talk about model. As I have told you repeatedly, I am saying that even if you have problem of heteroscedasticity, autocorrelation, or multicollarity, we'll discuss autocorrelation. We need to check specification issues. If you use the remedial action, despite that you find that you are unable to remove the problem or problem is still persisting, in that case, you should look at the specification, means the way you would have constructed the model which you are trying to test. If you rectify that theory behind the model or specification of the model, you will at times find that these problems go away on its own. So, after a point, when we do the modeling using econometrics, or for that matter, using anything, statistics, econometrics, or machine learning, the science gets over, and the artistic point of view comes into picture. Artistic means skill. So science gets over and skill comes. So specification issues are something of that league, where you have to think beyond the mathematics or statistics or econometrics, how best you can have a theory, how best you can solve a problem. And that is something which we call about specification. We have got reset test, which is, again, I'm repeatedly telling, not a great test, but something is always better than nothing. So using this, as I'm writing it optional, if you have got VIF calculated in descriptive statistics, you knock it out here. And if you have not done there, then you write it here. So at one of the places, preferably go into the descriptives. There are occasions, some models where descriptive becomes too clumsy. So we go for calculating VIF in the regression table. So choice is yours. When you are doing it, you can have your own choices and preferences. So in the note, this is also a good convention to describe a couple of things like null, which you would have used in the model, especially for diagnostic testing, describe here. So as we have removed autocorrelation, so I can knock out here also. I can remove autocorrelation discussion from note also. So this is partly a table which can be prepared whenever you are having the regression analysis. Many things can be added, many things can be deleted, but this in itself a complete picture. When we talk about regression, so this gives you a complete picture. Further, it can be enhanced, it can be, a couple of things can be reduced, but this in itself a complete story. Nobody, no analyst or no econometrician will say that the regression analysis is incomplete in any way. So up to this is the output of regression. 3 things we have made as we were discussing. First was descriptive table. Second, where is the table? This is the descriptive table. Second is the regression result. And third is the discussion. So we are left with prediction. I'll quickly tell you this also, how to go for prediction. So we'll move to the second part. So far, any issues to anyone? Any question?
Sir, can you show the H0 and H1 for the ESTAT for the RSET test? Reset test. Reset
That no specification problem.
Okay.
So we'll quickly move to prediction. I'll show you the caselet. Caselet says that if a student of height 185 centimeter, age 25 comes using the regression model, estimate the expected weight of that student, assuming he would like to be healthy. So if I show you what we can do quickly, we have got these. So both the things are there. You can use age also as an input, but age is not significant. So both are okay. You can have age as input. I'm not saying you can't, but you also know very well that only height is supposed to have its impact on the weight. So, but I'll take all three. I'll take it at Excel, right? So you are having this. Okay, I'll use it. And the for prediction, I have got the value of height, which is 5 centimeter, 185, and this is 25 years of age. So I can say this is the constant, and then it is the coefficient which is with height, and this is with the age. So minus 0.390, no, minus 39.09, and I've got minus 0.73, minus 0.26. So these are the coefficients which I have. All of you are with me?
Yes,
So I can have a prediction. So forecast or prediction value, forecast. So far, this is the constant plus height. I'm multiplying it with the height coefficient plus age with the age coefficient. That's it. All of you are with me? I'm just putting the data in the model. Yes?
yes,
This is the predicted value. 89.46 kgs is the predicted value. But if you remember my discussion, I told you that I'll give you a range. I'll give you a range, not only the single point estimation or point prediction, but I'll give you a range. To calculate the range, we will use some concept known as normal distribution concept or some concept of distribution, because right now we have T distribution, so we'll make use of T. I'll give you the context why I'm talking about T, because you have estimated T. So Z test, Anugamini will discuss with you. Z test comes into picture. It's a very remote case. What happened that when you know the variance of population, that is a typical situation when we use Z test. Z means completely normal distribution. So a best replica of perfectly normal distribution is T distribution. And unless until and 99% cases we do not know about the population, especially the variance of population. So we make use of t-test or t-statistics or t-distribution. What I have just said in last 2-3 minutes, you will find that as you move to inferential statistics in your stat course, you will be understanding my statement better. I think distributions have not started so far in stat, or has she started?
no, sir, not yet.
She will start normal distribution and she will talk about t-distribution also. Then she will go for sampling distribution, estimation issues. So you'll probably be able to understand that thing slightly better. So right now what I'm saying that I'm making use of t-distribution to arrive at a interval thing. So there are some functions. I'm using t and v function. If you can type t and v, the syntax you are finding that I need to put probability. So just because when we were accepting or rejecting the null, we were talking about level of significance of 5%. You with me? 5%, 0.05 is nothing but 5%. So that is, if you remember my discussion, initial discussion, the two tails were there, 2.5, 2.5% were at the tails. So, and those were the rejection region, and the middle area, which was 95% practically, that was increasing. So taking input from 5% level of significance, I'll have the probability of 5%. And degree of freedom, if you remember, degree of freedom, we have calculated here 7. If you remember, I have talked about degree of freedom. I said degree of freedom can be, degree of freedom is equal to n minus k plus 1. And n is the number of observations, k was the number of the independent variable plus 1. So this value 7 is coming. So whatever way, I have shown you in the output also of the, here, the 7, I said this 7 is also the degree of freedom. So whichever way you can understand or you can calculate, the best is you remember the formula when you are having multiple regression or simple regression. N minus k plus 1, n is the number of observation, k is the number of independent variables. Practically n is nothing but the constant. So this is the n minus k plus 1 will give you the degree of freedom. So coming back to Excel, so 5% logic I've explained to you, and I'm explaining to you the degree of freedom, which is 7 in this case. You will get a value. So what I'm doing right now, when I'm calculating the predicted value range, so range is equal to estimated value of B, beta, not exactly this, Y estimated, yeah, Y estimated value, plus and minus this T value at 0.05 or 5% level of significance into SE. Please note down this formula. This is nothing but the MSE, mean squared error, or the standard error of regression. I'll take you to the output again. So when I'm saying that SE, so I'm talking about SE of regression, SE of regression. This I'm referring to when I'm saying that I would like to use this item, standard error of regression, in calculating the range. So this is 6.04. So SE is equal to 6.04. T value we are calculating. I'll again take you to the Excel. So I can write down SE of regression is equal to 6.04. And this is the value of T. So if I give you the range, and I can calculate the range, range can be, this is the mean value which we have calculated. I'll go for plus first. This is the value of T at 5% level of significance. I'm multiplying it by, and the this is the, I think I've used plus here, plus, I'll go for minus mean value. This is the calculated value, predicted value, but point estimation. So I'm taking the predicted value minus this time. Again, I'll take the value of T statistics, multiply with the standard error. I've got this. So just let me, some people might be slightly confused. So these are the range. So I may say, instead of talking about one single value of the estimate or the forecast value, let's have a range. So this is something which is giving you, this is point, this is the range. So this fellow can expect to have, if he would like to be healthy, his weight should be in this range, or point estimation when you say then it should be close to 90 kg. I repeat myself what I have done. This value, if you look at here, this value is nothing but the, I'll again show you how I've calculated when I'm saying I need to calculate the T value at 5% level of significance. Logic I've explained to you, because we accept or reject the null, and this is a 5% level of significance. Formula is TINV. You are with me, class?
Yes,
TINV and then probability 5%, just because we are talking about 5% level of significance. Degree of freedom I've explained to you, n minus k plus 1. In this case, it is 7. I've entered, so I've got this value of t. So t value I have got, SE I have told you this is nothing but standard error of the regression, and this is the point estimated value as I have done. This I have calculated. If you look, remember, I have used the regression model to calculate a point estimate. So this is the way by which range can be estimated. So we can say close to 90 kg, or you can give 75 to 4 kg is the predicted range. I can answer the question in the case, as the case talks about the question. I can refer to that. Yeah, this, if a student is of this much height and this much age, then what would be the weight? So answer to that in a given format. So practically we have, with this we are winding up this caselet. Yes, can I move to second case?
So I have a doubt.
Yeah.
Yes, sir. So during coefficient analysis, we had established that a significant relationship exists between weight and height, and an insignificant relationship exists between weight and age. Right, sir?
Correct.
So, sir, when we are during prediction calculation, we should not assume beta is 0, because we are statistically we are assuming that there is no significant relationship, or should we use the coefficient standardized only?
Regarding age or height?
So for age, for the
What
insignificant
happened, it's a big question. I'll give you some analogy from the machine learning. When we talk about machine learning, we have got a black box. You never know. These type of detailed discussion cannot be done in machine learning because things are not clear. There is a model which is tried and tested, and it has got output. Output is telling you whether it is correct or not. So forecast values are estimated to check the sanctity of the model. So if I use that analogy, I can say that you put the age in the model, despite the fact it is not significant. But when you are having any discussion that which variable is going to have some its impact on height, whether height on weight, whether it is height or age, you will say that age is not having significant impact, but height is having the significant impact. So for discussion purpose, for any meaningful discussion or interpretation, you will say that height is significant, age is not. But when you are actually calculating the values, then I'll suggest that you have both, because what is happening, this r square value, after all, in the estimation it is contributing something. R square right now, this r square 71.24, this adjusted is 63.002. What you are finding, the 63.02% of r adjusted r square. After all, this is also taking some input from age, though it is insignificant. So for the betterment of the prediction, I'll say you have it, no problem. But for the conceptual clarity between height and age, which is having the meaningful impact on the weight, you will say it is not the age, rather it is the height. I hope I have answered your question. You can have
Yes,
follow-up
sir, yes.
questions.
So even for all other calculations as
So
well,
I'm
we are
talking about
considering.
reality and concept. So conceptually, what I'm saying, go by statistic thing, but when you practically calculate predicted value, go for taking both.
Okay.
We'll have some more applications of, I don't know, machine learning, Python. I'll corroborate what I just said. So when you apply concepts in machine learning, you do not bother which is significant, which is not, because issue of significance is not there at all in machine learning concepts. So they go by the predicted, the strength of prediction. If it is good, will they say that the model is perfect? Nobody talks about significance in machine learning. You understand what I'm saying?
Yes, sir, yes, I got your point, sir.
So, when you are becoming wiser, you have to be practical. Why should I say, no, I'm a student of, I'm a student of management. My job is to solve problem. I'm not a student of econometrics. My job is to solve problem. I'll go for a solution which solves my problem. So by taking age, whether it is insignificant, my problem can be solved better, I'll go for it. But I know I'm a wise person. I know that only height is significant, age is not.
Yes, sir.
So we'll go for tar rack caselet. Have you, all of you have gone through this caselet? Yes or no?
Yes, sir.
It was just half a page. If you haven't gone, I'll give you 1 minute. Just read it. I'll give you 1 minute. Read it. Those who have not read. I know some people must have not read. This is a caselet on tires, automobiles related thing. So what happened that the study is done to knowing that what are the propensity or inclination of people to buy the tire again. So they look at the tire from. I mean, the study says that they are doing the study keeping these two things in mind. What is the steering rates? I mean, the comfort when they drive fast and how much comfortable they are in taking turns. So steering rates, and then the opinion have been calculated from people regarding the tread wear. How do they rate the wear and tear of the tires? So keeping these two things in mind, the buy again decision, again the rating has been done. So I'll show you the data when I say. So look at this data. We are having some tire companies and they are having the rating on the scale of 10 is done, and buying again options would have also been calculated. And right now, so these three variables would have been estimated, or data for these three variables would have been gathered. Buying again decision, tread, tier, and steering rating, how much rating they would like to give. And everything would have been done on the scale of 10, so they are comparable. There's no problem of any transformation of data, because data is consistent across the board. All three data are consistent with each other. So we need not bother about changing or transforming the data. And we have got 18 observations. So here I'll go slightly fast. I think this again can be made. I can go to the commands. I can calculate. I'll go for regression. So regression results. I'll find out. So I'll take the data in Stata. So here I have got all the data with me, and I want to run regression. I would like to know how buying again decision, BA is the dependent variable, is going to be impacted by SR, steering rating, and tear and wear, and that's it. This is the result. And as you are finding, look at the p-values. So we'll go by again table. We'll stick to the table thing. Yeah, here it is. We'll say that tire racks caselet we are doing, and right now we'll quickly go for filling it. And as you are finding, look at here. So I'll just do this. You have any doubt, you can raise your voice by doing the unmute. So here what you are finding, this minus 5.39 constant value, minus 5.39 unstandardized I'm taking, and steering rating is 0.69, 0.69, rounding it off, and it is significant. Significant means, look at this corresponding p-value is less than 0.05. So if I give you again some recall, when we were talking about the beta, we said that null is beta beta is equal to 0, alternate beta is not equal to 0. I'm putting it J, so I'm generalizing. And remember, I'm not putting cap here, beta, I'm talking about the coefficient in the real model. So we are testing this hypothesis, pair of hypothesis. And to do that, I'll look for p-value. I'll check for p-value. If p-value is less than, this is what I told you to always remember, if less than 0.05, reject the null. So what we are finding here, the corresponding p-value is less than 0.05, which is 0.03. So reject the null, accept the alternate that it is non-zero, it is significant. So SR is significant. So when I say significant, I'll put one asterisk as I have done. And I'm going to x2. X2 is equal to 0.91. It is also significant. 0.91 significant. I'll come to it quickly. SE values are here. All three values are SE values. And so I'm not writing t-test. I look at t-test. These are the t-test. All three t values can be copied from here and put there. P-values also. P-values also you can copy from here and you can paste it here in the output. So this much portion is visibly clear to you. When we move to f-test, f-test is here. Look at the p-value of f-test. So again, the hypothesis of f-test is model is not good. I might have used different words, meaning would have been same. Model is okay. So what we are finding that corresponding p-value, this is the corresponding p-value of the f-test, which is again less than 0.05. So null can be rejected, alternate is going to be accepted, model is okay. So this model, if I look at what is the model, model is by again option is equal to point minus 0.39. Uh, 0.69 into, I think this is staring rate plus we have got 0.91 into wear and tear. So this is the estimated model. This is the model we have estimated. We have estimated this is the constant term. This is the beta 1. This is beta 2. This is beta 0. If I put it this way, y is equal to beta 0 plus beta 1 x1 plus beta 2 x2. So this discussion, you have got, anyone has got any discussion, any point which you want clarification? So coefficient analysis is completed. Anyone? Coming to latter part, the three things. If you look at the table, we have to find out f-test. I have just talked about f-test. F-test is 102.41. Significance is 0.00. Model is okay. Then next thing is R square. In bracket, you can put the adjusted R square value. Look at R square value is equal to 93%. Seems to be very high. Adjusted R square is equal to 0.92. So R square values are coming very high. But whenever R square is high, you should immediately check this correlation, CORR, pairwise correlation. And we have got, basically we are more interested, but we'll put all the three together. This by again, steering rate, and tear and wear. We'll talk significance 0.05. I'll correct if I'm wrong. 0.05 star. Wrong. So yeah, here we go. What we are finding that with the buying again, this is not important. What is important? SR and what we are finding. Look at here, the value is high. So this is a matter of concern. Please pay attention. SR and T, these two are the independent variable we are testing for correlation. What we are finding that the value of correlation coefficient is more than 0.8 and significant. So there is a serious problem of we have calculated VIF, or what you are finding VIF value is more than 4. Are you with me? Some people were talking about multiplicity problem. Are you with me?
Yes, sir.
Only Rajesh Shah, Tanay Rajesh Shah speaks. What about other people?
Yes,
Only
sir.
a few voices.
Yes, yes, sir.
Yes.
Concept is clear.
Yes, sir.
So here what we are finding that there is a problem of collinearity because these two independent variables are having the correlation coefficient which is more than 0.8 and significant. And I'm doubly checking by calculating VIF in Stata. You just type VIF after running the regression. Here we have run the regression. After that, I have run the correlation coefficient. And then I'm just writing VIF, I'm calculating. So VIF values are coming, which is more than 4. But VIF is always secondary. Primary thing is correlation coefficient between the independent variable. If it is more than 0.8 and significant, there's a problem of multicollinearity. So I need to advance my model. I need to drop one of the independent variables if I want a perfect model. So I'm not doing right now, but that is the obvious next step to cater to the problem or to remedy the, give the remedy to the multicollinearity problem. I need to do that. And immediately what you have found that when I see R square, which is very high, so you, in all likelihood, all the way you are going to check for multicollinearity problem because that is part and parcel of the format which I had developed for presenting the regression analysis result. By the time you would have got correlation coefficient as you calculate this, and here between the correlation coefficient, you between the independent variables, you find the correlation coefficient which is more than 0.8. Immediately you will say, so by default, you will find that here I've added minima maxima also in descriptive that you can all the way add. So back to the discussion. So R square, from high R square, it prompted me to revisit the issue of multicollinearity. It is there, so we need to check. We need to remove one of them, and we'll find out which is going to give us better. When we say better means this error value, if it is 0.7, and then we'll run the. Let me try to do it. I will be, deviating, so I'm not doing it right now. Let me finish at least this whole analysis, but one by one, I'll check steering rate only, I'll check wear tier only, and I'll see where my R square is high, where my standard error of the regression is low. That model I'll go for. So here, my, yeah. So SE of error, I can easily calculate. I can easily find out this is 0.5727. I can take for regression, standard error of regression. Degree of freedom, you remember we talked about equation. What was the formula? There are 18 observations. So degree of freedom formula was n minus k plus 1. N was 18, k is equal to how much? K is equal to 2 plus 1, so 15 would be the right degree of freedom. So as you're finding, 15 is coming here, and when you have to write, you need to write 15. Observations are 18, and autocorrelation again can be knocked out. We can go for heteroscedasticity. E is that H test. And what we are finding, there is no problem of heteroscedasty. Remember, we have discussed H naught, no heteroscedasty. H alternate, yes, there is heteroscedasty. So this is the pair of hypothesis which we are checking. And what we are finding that p-value is coming out to be of ST test, which is more than 0.05. So I have no choice, but I can't reject the null. I have to accept it. So no heteroscedasty assumption or homoscedasty issue is accepted. So no problem of heteroscedasty in this data. Then again, I need to test for specification. OV test. OV test is significant. So there is some problem of specification. As I have right now talked, there is a problem of multicularity, and that is reflected in reset test. Reset test, we look at p-values 0.05, less than 0.05. And for reset test, we had this no specification problem. So when I'm finding in this result that p-value of reset test is 0.012, which is less than 0.05, so null is to be rejected. So I can't accept this no specification problem null, rather I have to say yes, there is some problem of the specification. As we have seen, there is a problem of multiplicativity, but this is not full and foolproof. It may sometimes give you, it may sometimes not give you. So everything individually needs to be tested. It's not that you have got RSET test and get to know there is some problem of diagnostic testing or some problem of heteroscedasty, autocorrelation or specification. So this was the table. We have got regression table. So all these tests, and again, if I have to go for prediction issues, predict the buying rating of steering is 0.62 and 0.62 in both cases. So predict the buy rating of the buyer. If the tire rating is 6.2 and VAT rating is 6.2, calculate the range also. I'm trying to answer this. So this is the model which we have estimated using the tire rack. This is the model we have estimated. So if I have to calculate the value, then I'll take this model to Excel so that I can calculate the values. So again, constant is equal to constant value is 5.39, and I've got steering rating, wear and tear 0.69. This is 0.91, and then the tire 6.2 for both. So to predict, I've got values of steering rating and wear tear as 6.2, 6.2, and 6.2. So I am predicting. So predicted value, if I have to calculate, I'll steering rating coefficient plus wear tear into the value of wear tear for this given situation. I've got a rating of 4.53. I have to calculate range. So I'll calculate t value to calculate range. I have to calculate t value. So I'm calculating t value at 5%. So to calculate that, I'm t value T, I, and V. I'm going for range calculation. So this will remain same. Degree of freedom, we have just calculated 15 by n minus k plus 1 formula. Here I go. So I'll go for lower range and higher range. So to calculate lower range, I'll take the predicted value and put minus t value, and the standard error value was this value is 0.5727. 0.5727. Here I go. And similarly, I can calculate the upper value, high value. I'll take this and I multiply it by 0.5727. Here I go. So these are the three estimates. So with this, I have practically finished the entire RACS caselet also. CEO salary we couldn't do, so I'll give the solution of these two and I'll share with you maybe tomorrow or on Sunday. Before next class, I would insist that you at least go through. You do it on your own. Yeah, right. Hello? Hello? Am I audible?
Yes, sir.
sir.
You're
Yes,
audible.
sir.
Somebody was asking something. Please feel free. Okay, so we'll take a break for today's class. We'll have after 5 minutes we will start the quiz. So I'm sharing with you the first of all I'll stop the sharing option. So no, you can't see my screen now.
Yes, sir.
You can't see, sir.
No. Yes.
No.
No, sir.
So I'm sharing with you in your chat box. So after 5 minutes, exactly at 1:35, it will. I'll open it. It will be closed exactly after 5 minutes, and I am believing that you have a fair amount of understanding of using the uh, form in Microsoft Office. You would like to say something? No? So as Sai madam was talking that you have to use only the Microsoft Office connection. You have logged in, all of you? All
Yes,
of you
sir.
have logged in using
Yes.
your Microsoft official login password.
Yes,
Please
sir.
understand, there is no possibility of retest. If you are unable to do it, I'm very sorry, there is no option. University does not allow for any retest. So we do everything before the test. So you have any problem, any connectivity issue, login password not working, tell right now, not post test. After quiz, nothing, we won't be able to listen to anything. Any concern right now you share. Sai madam is just here to help you if you have got any problem.
Sir, do we need to perform anything on EBUs or Stata?
No analysis, no analysis. Only, I mean, whatever we have discussed, that knowledge is good enough. That
Sir,
knowledge, no application of any software, neither Excel nor EU nor Stata, nothing. Okay, so I'm sharing first of all, and अच्छा, ये मैंने जो है I have shared the link. Form is still not active, but you can log in. You can be just ready. Exactly after 3-4 minutes, I'll make it open, and then exactly after 5 minutes, that will be closed. So the form is still not open, but you can access it. Access through browser, not through mobile or through any other thing.
Sir, can you give us a warning when there is 1 minute left?
Sure, we'll do that. So you do everything, you just be ready. Yeah, saying Akash, tell me.
Yes, no, sir. That's it, sir. Thank you.
Yeah, okay. Carry on. मुझे ये करना है सर। इसका टाइम बच रहा है। पाँच मिनट 6 सेकंड लेते हैं, कोई बात नहीं। So I'm just making it active. So I have got 5 minutes 6 seconds. I'm giving you practically 5 minutes 6 seconds. I mean just extra. So I'm using timer. So no dispute of time. So I've activated. Yeah. Now you refresh and you will find that it's working. Now quiz is active. दो देखिए. Last 1 minute. I repeat, last 1 minute.